to and all present here. I welcome you to the 47th episode of Gyaniki Tech Talks, and we see that the energy demand in EV powertrains is increasing. As a result, there's the need for high voltage batteries. So that electrical safety also becomes a very important decision factor that we all have to take care of. In the session today, we'll discuss about isolation management in the context of Indian EVs. And today with us we have Mr. Ameya Gambhir, who is the head of Advanced Engineering and Hardware Development at Hella India Automotive Private Limited. Mr. Gambhir has rich experience of 18 years working in organizations like L&T, KPIT, TCS, and Bros. Before his work in Hella, where he's played a very crucial role in the development of motor control, power electronics, and more. At Hella, Mr. Gambhir is leading a team of 25 engineers with vivid competencies such as power electronics, modeling, and simulation, etc., while playing a very vital role in the pre-development of projects in connectivity, electrification, and driver assistance. Mr. Gambhir has 4 research patents published and about 7 technical papers published in organizations like SAE or IEEE. It's a pleasure to have you with us today, sir. I welcome you on behalf of Team Gyaniki and all the participants.
Yeah. So first of all, thank you, Gyaniki, for providing us an opportunity to present one of the important awareness topic in isolation management. So let's look forward towards this presentation, and I'm also happy to see a lot of industry people participating in this forum. So I'll be really glad to have the interactive session today. So let me share my screen. All right, I hope you are able to see my screen.
Yes, sir, you can go ahead.
Yes,
So good morning again. Today we are going to discuss about isolation management for Indian navies. This is one of the most interesting topic. At the same time, it is one of the least talked about topics based on whatever interactions I have had with industry, with customers, with tier ones, as well as with regulatory bodies. Maybe before we start, I just wanted to say it loud that whatever images or references or sources that I have used, they are only for the explanation purpose, because some of them could be the screenshots from international standards as well. All right, so let's start our discussion with the context of India. And when we always discuss this topic with our customers, the high voltage safety considerations, isolation management, typically it is my experience that the overall awareness in India is little lesser compared to Western world. And that's the reason why this got us motivated for discussing this topic with you all. So the very first trend that we are all witnessing in India is the e-mobility trend. Government is pushing this. Different startup OEMs are entering into the market, and it started with two-wheeler and three-wheeler product segment, but now we are seeing that it is gaining momentum even in the passenger vehicle domain, and very soon this will enter into LCVs and then uh, commercial vehicles as well. But at the same time, what we are observing as an industry player, as a tier one player, is many customers are now approaching us and asking us to migrate from the low voltages to high voltages. So typically the customers who were using 48-volt battery packs are now trying to adapt to 60-volt battery packs or 60-volt to 72-volt migration. 72-volt to 96-volt migration is happening. This is mainly because of improving the performance of an electric vehicle, making it as appropriate or as compatible as the performance of IC engine vehicle. And the other reason for increasing the voltage rating is also to reduce the cost of copper, because of higher currents at lower voltages. Cost of harnesses, cost of bus bars is phenomenally high. So this is one of the reasons why we have to think of isolation management in the Indian context more seriously than before. Another factor is the environment. In India, we are all aware that we have different regions with extremities like humidity or heat or cold, or even whenever there is a heat, there is an effect of ultraviolet. So basically all of this is actually causing damage to typical insulation. The image that you see here is the effect of corrosion on a printed circuit board. You can imagine the kind of clearance and creepage which was developed at the design stage after the weathering effect, it is no longer existing. Next important part in Indian context is the monsoon and then the waterlogging. As the situation is very evident in cities like Pune, every year we experience couple of days of waterlogging. And imagine these vehicles which are stuck in traffic, which are submerged in water, are electric vehicles. And that too, not the 48-volt electric, but the high voltage electric. So the safety of occupants as well as the safety of nearby or the road traffic participants is also quite important. Next topic that is again related to our environment and our demography is the rodents. In many parts, for example, cities like Mumbai, Chennai, during monsoon seasons, the rodents enter into cars because uh, because of the water ingress, and then when they enter into the cars, then we all know the effects. They could damage the insulation, and imagine this insulation is that of a high voltage cable inside an electric car, so it could create a disastrous effect. We also have the increased number of minor accidents in India. If there is a major accident, there is a tendency to take the car to service station, but minor accidents many times these are treated by untrained garages. These people who are having a lot of it's an unorganized sector here. They do not have adequate means and know-how to take care of high voltage safety. We also have the aging effect of the vehicle, which will eventually create a loss of isolation. And then, yeah, most important thing is the fire hazard. So I've shown you a symbol here. So this is the international symbol for high voltage safety hazard, and this is for the fire hazard. Basically, these two things are interrelated to each other. A fire hazard could result into a compromise of electric safety or vice versa. And in the last couple of weeks, we have witnessed that some of the renowned brands also were suffering because of fire hazards. So I'm talking about the electric two-wheeler industry. Fortunately, they were all using low voltages, but imagine if this could happen in a high voltage EV, this could really be a disaster. All right, so now after we discuss about why isolation management is more important in Indian context, let's discuss about what happens if there is a compromise, because this is very commonly asked question and very I mean, I have seen people in the industry also, they have different opinions. So first of all, let me clearly clarify this, that the electric shock hazard that we all experience is not because of the voltage, but it is because of the current. And obviously the voltage and currents are proportional, but many people started working on this topic in the last couple of decades, and finally we have an IC standard, IC 60479-1. So this standard talks about the equivalent body model for human being. We have a DC resistance of the skin, and then we have an impedance of the skin, which is represented by a parallel combination of resistor and capacitor. And different touch points, for example, hand to hand or hand to shoulder or hand to feet, may have different values of R1, C1 and R2. So all said and done, why I wanted to show this slide is to maybe clarify that a human will have a varied degree of impedances, and it is also a factor of frequency. So as frequency increases, the impedance of the human body reduces. This is also the reason why our body is more immune to higher amounts of DC touch currents as compared to the AC touch currents. In the next slide, I am going to again discuss about the hazards which are associated with varying degrees of currents. So here, this is talking about the effects of shock when we come in contact with high voltage AC. Y-axis of this graph is showing the duration of contact, and x-axis is the current that is flowing through human body on the basis of the R1, R2, and C1, the equivalent body impedance model that we saw in the last slide. So this table is taken again from the same IC 60479 standard. It shows that from 0 to 0.5 milliampere of AC current, we are in a safe zone. So this is the AC1 zone. As the current increases, so we are in AC2 zone, but we still do not have any dangerous physiological effect because of that current. So you can see the current is ranging from zero point 0.5 milliamperes to up to 200 milliamps. But at the same time, we should also look at the y-axis. So probably we are able to survive with 100 milliamps of current passing through our body, but then for how long? May not be for more than 30 milliseconds or so. If the duration of the current is longer, then obviously you can see that probably we can survive a shock of 10 milliamperes of current flowing through our body for a period of say 5 to 10 seconds or so. Then we go to the next zone, which is AC3, and this is where the severity starts increasing. So in AC3 zone also, there is no organic damage, but there is a possibility of muscle contractions and breathing difficulties. So we call this as a let go threshold. That means beyond this threshold, probably we will not be able to control our own muscles and we may not be able to let it go if accidentally we are holding a conductor which is live. So reversible interference in the formation of cardiac impulse propagation without ventricular fibrillation, sorry, and increasing with the intensity of the current and the time for which the current is flowing. So this is like say a border between very hazardous severe situation and then the normal injury. But then the next zones AC4, and again this zone is divided into three, will be really life threatening. So if you see AC 4.1, there is a probability of ventricular fibrillation. Basically, this is talking about this current is going to stop the functionality of our heart because our heart also requires an electrical impulse. And if that sinus node in the heart and this current that is flowing through our body, if they interact with each other, then this might result into a severe cardiac arrest. So 5% possibility, 50% possibility, and then more than 50% possibility of ventricular fibrillation, which is in other words, a possible death. So all said and done, we should be playing in the green zone. And this is where the isolation management system should give us an alarm if the currents, the leakage currents we are talking about, are going to cross from AC1 to AC2 or more dangerously from AC2 to AC3 zones. Now, this was the case of alternating current, the 50 hertz or 60 hertz or even higher kilohertz in switching regulators in motor inverters. But what is the case of DC current here? So again, I borrowed the graph from the same standard, the same scale for x-axis and y-axis. But now you can see we are able to survive up to 2 milliamps of DC current flowing through our body without any serious injury, or rather without any uh, injury. There is just a pricking sensation for DC1 zone. For DC2 zone, there is a possibility of involuntary muscle contraction, especially when making, breaking, and rapidly alternating current flows through our body. But again, this is not going to be harmful electrical physiological effects. So in other words, we are able to, let's say, withstand 20 milliamps of DC for a period of 5 to 10 seconds or so. But to be on a safer side, we always consider that any current, any DC current which is more than 10 milliamps should be treated or should be avoided in the IMD. And then the next zones are probably similar, that as you go towards more and more current on the right side of the x-axis, there is a possibility of life-threatening hazard. All right. So we discussed about the currents of the effects of AC as well as DC current. We understood that it could be life-threatening, and we also understood that it is not the voltage, but it is the current finally that matters in our injuries or even further hazards. Now I'm going to discuss about the definition of high voltage, and I always come across this confusion also while discussing with industry folks, that many people do not really know what is really the high voltage because different standards, and you can see here different standards also confuse us a little bit. So we have low voltage, medium voltage, high voltage, and extra high voltage, which are defined here. And you can see the National Electric Code of India defines less than 250 volt as a low voltage, whereas IC 60071 says less than 1 kilovolt as a low voltage, and some other standards define some other values. Okay, my intention is not to compare the standards with each other, but I just want to bring your attention to what is the definition of high voltage in our industry. That means in automotive industry. So the definition is derived from the UN standard ECER 100, and which is also available in the USA standard, the FMVSS 305. So in our industry, anything which is below 60 volt DC or below 30 volt AC RMS is considered to be low voltage. And anything which is between 60 volt DC to 1500 volt DC or 30 volt AC to 1000 volt AC, again this is RMS, is considered to be high voltage. And yeah, we are not discussing about extra high voltage here because most of our systems, including battery voltages, including inverter ratings, onboard charger ratings, and all are going to fall in the definition of high voltage. This is the international symbol for electric shock hazard, and as per regulatory requirements, the symbol is required by the automotive OEMs as well as tier 1 suppliers to be provided wherever the user is going to possibly touch an unexposed conductive part in the vehicle subsystems. So important takeaway for us is we need to ensure that whenever we are dealing with greater than 60 volt DC and greater than 30 volt AC, we need to take care of isolation management, whether it is at OEM level or whether it is at tier 1 level. All right. So now I'm going to discuss about some of the regulations which are governing isolation management. And I have listed both the international regulation as well as Indian regulation. So ECE R100, which we saw in the last slide, is talking about a uniform provision concerning the approval of vehicles with regards to specific requirements for electric powertrain. Part 1 talks about the requirements for category M and category N vehicles, the electric vehicles, basically where their speed is greater than 25 kilometers per hour. So basically these are the passenger and commercial vehicles. Whereas part 2 of the ECR 100 is talking about the safety requirements for tier 1 supplier, basically the supplier who is providing the renewable electrical energy storage, REESS system. So in other words, this is a system which comprises of battery management system and some of the subsystems, maybe part of onboard charger as well, which is going to create the universal set of REESS. And then I've listed some of the annexures in this standard, which are having a reference to isolation management. For example, Annex 5A is talking about the isolation resistance measurement method at vehicle level. Annex 6 is talking about the onboard isolation resistance monitoring system. Annex 7 is talking about verification of the isolation resistance. Then let me talk about AI 038. So this is the regulation again for the same category of vehicles, passenger and commercial vehicles. And this regulation is derived from ECR 100. Whenever we are dealing with any regulation, we should always take care that we are referring to the most recent part of the regulation. For example, ECR 100, we are having revision 2 and amendment 5, which was in July 2021. AI 038 was also recently revised in 2021. And it is in revision 2 state. So part 1 is similar to ECR 100, which is at vehicle level, and part 2 is at battery and BMS level. We have similar annexures talking about the isolation resistance measurement method, isolation resistance monitoring system, which is on board, the method to verify this system, and then confirmation for or verification method for testing authorities. So it is quite similar to ECR 100. Then we have another set of standards, which is for category L vehicles. So basically the two-wheeler and three-wheelers, which is the predominant electrification segment in India as on today. So again, this regulation as far as isolation monitoring is applicable only when we are going to have a powertrain which is having a working voltage which is above 60 volts DC, as we just saw in the last definition. So as long as the vehicles are working with 48 volt battery pack, which is typically the case for low speed vehicles, probably these regulations are not applicable with regards to isolation management. Then we have AIS 156 regulation, again, which is derived from the ECR 136 regulation, which is applicable for category L vehicle, which are the two-wheeler and three-wheelers. So our focus is on ECR 100 and AIS 038, which are currently seeing a use case because most of the PVs obviously have voltages which are above the definition of high voltage. All right, so we just saw regulatory landscape, but let's also look at the standards because standards is they're always one step ahead of regulations. And of course, regulations will follow standard eventually. Let me give you a glimpse of some of the standards which are again related to our topic of interest isolation management. So we have IC 60479-1. So this is the standard which I already talked about, which talks about the human body model. And it also talks about the classification of severity levels for DC as well as AC shock hazards. Then we have 6469-1. So this standard basically talks about the onboard rechargeable energy storage systems and electrically propelled vehicles. So again, it talks about some of the isolation management techniques which are required at vehicle level. We have part 3 of the same standard, which talks about protection of persons against electric hazard. So isolation resistance measurement for voltage class B2 electric circuits. Test for isolation resistance monitoring system and touch current specifications are listed in ISO 6469-3 standard. And when they have very special standard, which is, let's say, targeted towards insulation monitoring devices, which is IEC 61557-8. So the part 8 of this standard is talking about insulation monitoring device for IT systems. We are going to see what is an IT system and also the automotive context of this. So basically the standard talks about different types of IMDs, their requirements, the DC IMD, the AC IMD, as well as the IMD, which is required for a combination of DC and AC subsystems in an electric vehicle. So we saw regulations, we also saw standards. Now let's look at the specific clause from Indian regulation, because this is also one of the common questions which are asked by OEM. That let's understand what is the isolation resistance that is allowed, and which is, or in other words, below that we have to raise an alarm. So as per our Indian regulation, which is again derived from EC R100, the European regulation, for DC buses, 100 ohms per volt is the limit. So this is the limit for working voltage. And for AC buses, it is 500 ohms per volt. So in simple words, if you're using a, say, a 96 volt battery, then this becomes 9.6 kilo ohms. That means when your isolation resistance between any of the live part, for example, HVDC plus, HVDC minus, and then chassis of the vehicle, when that resistance falls below 9.6 kilo ohm in this example, then your isolation monitoring system should come into picture, and then it should raise an alarm or it should take a corrective action. Maybe disconnect the battery pack from rest of the vehicle. This standard also talks about the need for galvanic isolation. So whenever you are dealing with high voltage systems, it is mandatory to have galvanic isolation between an LV system and an HV system. An electric car will still have a 12-volt lead acid battery, and that is the definition of low voltage. Typically, this 12-volt lead acid battery will also be connected. The negative of this battery will also be connected to chassis, and chassis in an electric vehicle is also considered to be earth, or basically an equipotential bonding. There is a requirement for the standard that all exposed conductive parts should be connected to vehicle chassis. The standard also talks about what is the maximum allowed resistance between any of the conductive part and chassis of the vehicle. So in other words, the standard is basically encouraging that your chassis should act as an earth. It should be connected to low voltage ground, and between any of the high voltage systems and low voltage systems, you should maintain galvanic isolation. What is galvanic isolation? Basically, we are talking about a complete separation of the two domains, the LV domain and HV domain. No currents of these domains will either interact with each other unless and until there is an isolation fault. The standard also talks about need for isolation measurement and monitoring. But here there is, let's say, one thing that I observed about the standard. For vehicles which are having fuel cell based systems, the standard clearly mentions that these vehicles should have an onboard isolation monitoring device. But for the rest of the vehicle category, which are basically the predominant category in India, the standard talks about the ensuring the isolation by means of calculation or by means of measurement. But I hope that in future the standard will also make it mandatory to have isolation monitoring devices in electric vehicle. And the reason is the first slide that we discussed, the Indian context. There are so many reasons which are likely to create an isolation fault in a vehicle, and this will not happen at the time of delivery of the vehicle, but this is an aging effect or slowly occurring effect. By the way, the standard also talks about, or in other words, I have also derived the currents which are based on the standard. So basically, when we are talking about 500 ohms per volt, we are talking about less than 2 milliamps of current that is allowed through body for AC. And when we are talking about 100 ohms per volt of isolation resistance, we are talking about less than 10 milliamps of current that should be allowed to flow through human body. So this is in correlation with what we just saw in the international standard. This standard talks about two sections here. This section is talking about direct current or alternating current buses, and this talks about the combined DC and AC buses. So in some vehicles, for example, some vehicles may use transformerless onboard charger. In such a scenario, there is a possibility that the DC systems and AC systems in the vehicle may be galvanically connected to each other. What are AC systems in a vehicle? Basically the charger input. Sorry. What are the DC systems in a vehicle? Basically the high voltage battery and then all other parts which are connected to high voltage battery. For example, battery management system. For example, traction inverter. For example, DC-DC converter. So if a vehicle is having a transformerless onboard charger, then this requirement will be applicable. If a vehicle is having already a galvanic isolation between AC and DC systems, then this requirement will be applicable. Okay, so now let's talk about isolation management. So far, we have seen the need for isolation management. We have also seen the regulatory bodies. So isolation management is divided in three basic categories: the prevention part of it, detection part of it, and sorry, the corrective action part of it. The prevention of isolation management is part of the design, and this is done using different types of insulation. So we are going to see these insulations in the next slide. The detection part is basically the focus of our tech talk today. So whatever have we done so far for preventing it, let's say because of any reason, if we are not able to manage it, then the detection part comes into picture. And the detection part mostly relies on measurement of the leakage resistance. So the leakage resistance between any of the high voltage lines to vehicle chassis. Vehicle chassis is considered to be earth for our measurements. And corrective action is again decided by some other issue. It could be an alarm, or it could be the battery disconnection in case of first fault or second fault. People also confuse between isolation and insulation. So just for a quick reference, isolation is basically keeping the two things apart. So as I said, LV domain and HV domain. So it's not a thing, but it's a concept. Whereas insulation is a substance that provides isolation. So basically, insulation is one of the techniques for preventing the isolation fault. Now, though our focus of this tech talk is on the detection part, but let me quickly mention what are the insulation types, because this may also have certain dependence on selecting the right kind of insulation monitoring device. So we have functional insulation, basic insulation, and then for the advanced part, we have supplementary, double, and reinforced insulation. What is functional insulation? Functional insulation is basically to ensure that the correct operation of product. This does not take care of electrical safety of user in mind. For example, if I'm designing a 96-volt battery management system, then what should be my distance between two PCB tracks? What should be the creepage distance? What should be the separation of wires or connector pins from each other, so that there is no arcing or sparking possible? So this is decided by functional insulation. There is no protection of user in mind. Then we come to basic insulation. So we have single layer insulation or single layer insulation for protection against high voltage hazard. For example, rubber insulation around each pair of an AC cord. This comes under class 1 of the protection along with protective earth. So most of the equipment that we use are having basic insulation. But whenever there is no earth terminal available for protective as a protective earth, then we need to take help of the additional or the advanced layers of insulation. So supplementary insulation is basically one additional layer of insulation which is independent of basic insulation. For example, plastic use of an external power supply. Double insulation is a combination of both basic as well as supplementary. And reinforced insulation is whatever you could achieve with these two layers. If you can achieve it with a single layer, then that is called as reinforced insulation. So basically the devices that we use for maintaining galvanic isolation between LV domain and HV domain, they fall under the reinforced insulation category. So for example, optical isolators, magnetic isolators based on transformer or capacitive coupling. So that comes under the protection class 2 equipment. So this was just an introduction about the preventive part of isolation management. Now let's start about the detection part. And as I said, automotive systems have been derived from industrial systems. High voltage is just a couple of decades in the automotive industry, but as we are all aware, for industrial domain, high voltages are not common, not new. They have been in existence since many decades. So I'll not take much time on this, but my motivation of showing this is to appreciate the fact of what is the earthing system in India and how it is linked with isolation monitoring device. So we have three major systems in the world: the TN system, the TT system, and IT system. So these systems are basically talking about how we receive electricity in our households from generators, distribution, and other systems. So every system, for example, the first letter talks about the T letter in TN system or in these systems. It talks about this neutral terminal, whether it is directly earth. If it is directly earth, it is called as T. And if it is not directly earth, then it is called as I. The second letter of this system talks about how do we treat the ECP. ECP is basically the exposed conductive part of our equipment, whether we connect it to neutral or whether we neutral is connected to earth or not. So based on that, these three systems exist in the world. Now, each system has a different mechanism to detect the isolation fault and then to act on it. This is also one of the common questions that I hear. People ask me that why can't we use MCB in an electric vehicle, or why can't we use an RCD, the residual current device, in an electric vehicle. So basically MCB is used in a TN system. You can see that if there is an isolation fault, then the currents which are flowing through that fault line will be more than 2300 amperes in this example. So obviously this will require a tripping of overcurrent protection device, and one such device is the circuit breaker. For an TT system, we use RCD, the residual current device, because here the currents are relatively low. And then for an IT system, we use IMD. So IMD is required for an IT system, and let's discuss in the next slide how it is related to our industry. So this slide also gives a picture about what is the common earthing system in India. So in India, as per IS 3042 standard, we are following TNCS standard. So basically this system. So now let's have a look at the IT system, the fault tolerance of IC system, because this is an important part for IMD. So the beauty of IT system is the availability of power is ensured at the maximum. So just one step back, in a TN system, if there was an isolation fault, there may not be a hazard for electric shock because the short circuit is happening through wires, but then there is a power unavailability. Whereas in IT system, the system is designed to have maximum power availability, of course, at the cost of a possible electric shock hazard, but that too, not in the first fault, but in the second fault. So in this system, what will happen if there is a compromise in isolation due to unearth neutral, very small current flows and the operation of the system can continue. That means there may not be a electrical shock hazard when the first fault occurs in an IT system. Okay, but it is expected that this IMD, which is sitting here between neutral and earth, it should detect this and it should also locate the fault. If we are able to eliminate the fault as early as possible, then there is no chance of creating a second fault. Now, in an IT system, let's consider that the second fault occurs. So first fault has already occurred, but probably it got undetected and there was no harm. But now in the second fault, there is a very uh, high danger of short circuit as well as harm. So you can see the currents in the second fault, because now second fault is directly creating a short circuit. The currents could be as high as 2300 amperes. And basically, if the fault occurs in another line, then there is a short circuit hazard. Automotive systems are derived from IT systems, and that's why whatever measures that are followed in the industrial domain for IT systems are applicable in our domain, the automotive domain. So now let's look at an electric vehicle architecture. And this is from the point of view of isolation and whatever, wherever there are possible leakage resistances. So this is the electric vehicle charging inlet. The phase neutral and earth is shown here. So there is a combination of R and C, the RAC and CAC, which is basically a leakage resistance or leakage impedance, basically a pair of resistance capacitors. This is the leakage impedance between phase to earth and neutral to earth. Then we have this typical onboard charger, which is there in the vehicle. So this shows we have an onboard charger, which is having a galvanic isolation between input and output. Then we have the output, which is HVDC plus and HVDC minus rail in the vehicle. We still have a possible leakage impedance between HVDC plus to chassis and HVDC minus to chassis. So this line, which is shown with yellow and green dots or dash, this is basically the protective equipotential bonding or electrical chassis of the vehicle. As we just saw in the regulatory requirements, all conductive parts of the vehicle have to be connected to chassis, and this is our earth. So whenever we are talking about leakage, the leakage is between any of the high voltage system and earth of the vehicle. There is a possibility of this leakage resistance between high voltage battery to earth, low high voltage battery to earth. We also have possibility that, so this is the inverter of the vehicle. We also have possibility that any of these three lines which are given to a three-phase AC motor, there is also a possibility of complex impedances and then leakage impedances between high voltage to chassis. We also have an isolated DC-DC where also there is a possibility of leakage. So why I wanted to show this diagram to you is the appreciation of the fact that an electric vehicle subsystem is highly complex. There are many possibilities of fault, and the fault is not just resistive in nature. It is a complex combination of R and C's. So it's very difficult to find out the exact value of the isolation resistance in a given time. And this shows a concept diagram of an IMD, which is sitting between chassis and the high voltage systems here. We'll be discussing more on this in the next slide. Before that, let's also discuss the asymmetrical and symmetrical faults. So this shows a diagram where the two high voltage lines and then protective earth is connected through an IMD. So whenever there is a fault between one of the lines to earth, we call it as an asymmetrical fault. Whenever there is a fault between both the lines to earth, and if the fault resistance is also same, then that is called as a symmetrical fault. Why I'm talking about this? Because this has a reference to some of the disadvantages of passive IMD systems that we are going to discuss in next slides. The IC standard, which I mentioned before, is for IMD purpose only. It specifies that the requirements for insulation monitoring devices, it should support a prescribed measuring principle which enables them to monitor both symmetrical as well as asymmetrical faults. So even if both the leakage resistances are same, the IMD should or must be able to detect that as a symmetrical fault scenario in an electric vehicle. Okay, so this is the IEC 61578 standard. So I understand this may not be readable, so I have just taken a summary of this. Basically, this standard talks about response time for AC as well as AC plus DC system. This standard tracks about peak value of the measuring voltage, measurement current range, impedance range, basically AC impedance and DC resistance range. So this is basically the master standard for the insulation monitoring devices. Now let's talk about the basic IMD that many tier ones have implemented in vehicle. Mostly this is part of battery management system. So we have two measurement methods to have an IMD. So basically this is the high voltage line, let's say battery positive. This is the low voltage line, which is battery negative, and this is the protective earth terminal, which is shown with this color. And RF plus, RF minus are basically the leakage resistances or fault resistances. So in the first method, which is called as an imbalance method, it is based on the principle of Wheatstone bridge. You can see R1, R2, and R3 resistors. So the disadvantage of this system, though it looks very simple in implementation, the disadvantage is it can only measure asymmetric faults. If the value of R1 and R2 is exactly same, then there is no way possible to find out if there was a leakage because of RF plus or RF minus or both. Then the next method is 3 voltmeter method, which was also very popular in the industry. So basically this method has these three switches and these 3 voltmeters. I will discuss more about this method in the next slide. Both these methods depend on the system voltage, and both of the methods expect that the system voltage, basically the HVDC voltage UN, is stable. But unfortunately, when you are driving a vehicle, you know that the voltage cannot be stable because of various loads switching on and switching off asynchronously. There is no fixed DC voltage on the HVDC line. The voltage will keep on fluctuating, and that will make these measurements either ineffective or highly complex. So let's look at the popular method, the 3 voltmeter method, which is used for isolation monitoring. And why this is called as passive isolation monitoring? As I just said, this method requires a constant DC voltage. If the DC voltage is fluctuating, then obviously there will be an error in the measurement, and either the system may not be able to measure the fault resistance RP or RN shown here, or it will require some software adaptations. So basically, let's understand how the passive isolation monitoring system works, which is, as on today, most commonly used method. So in the first step, switch S1 and S2 are open. This is the S1 switch, which is connecting R1 between HVDC positive and chassis, and S2 switch is connecting the HVDC negative and chassis through R3 and R4. So first we only close switch S3. Basically by closing the switch S3, we basically sample the line voltage at that instance. Then in the next step, we close the switch S2, and then we measure the voltage which is between HVDC negative to chassis. In the next step, then we close switch S1, and then we measure the voltage between HVDC plus to chassis. And on the basis of this, and considering the RP and RN are unknown values, we try to estimate these values using internal equations. And then we basically we compare these values with the regulatory requirement. For example, if you are using a 96 volt battery pack and if the regulation says that your isolation resistance cannot go below 10 kilo ohms, then you can have a safety margin and you can then raise an alarm. So basically this method will meet the IC 61578 requirements. Both RP and RN can be measured. But as I said, the challenge with this method is complexity because of changes in the DC voltage. It will work only when the HV battery potential is stable. That means vehicle is not moving, and only work when HV is powered on. It cannot identify the faults between inverter AC output and chassis. So as you see, most commonly this is part of the battery management system, and this can work with DC lines. Now imagine in our earlier diagram, if there was a fault in any of these three lines to chassis, then this method that we are talking about, the passive isolation monitoring, may not help us. All right. So what is the solution? So we know the disadvantages. though it is common method, but we know the disadvantages. So the solution is an active isolation monitoring system. So here, this system basically works on a fact that there is an electric impulse that is induced into the high voltage line by an active device. So I have borrowed this screenshot from Bender, who is a world leader company in isolation management, both or rather in all domains, medical, industrial, aviation, automotive, and they have a patented technology, and this technology can work for both AC as well as DC systems, symmetrical as well as asymmetrical faults, and it fully meets the IC 61557-8 requirements that we just saw in the screenshot. So basically they call it as AMP, the adaptive measuring pulse. This device here, generator, creates an impulse. That impulse is fed into the line, and then if there was a leakage resistance between any of the lines to chassis or both lines to chassis, then the same signal will be measured back by the system here. And then it will use some internal filters just to avoid the effects of 50 or 60 hertz noise or the switching noise of DC-DC converters or inverters. And then this system will be able to estimate accurately what is the isolation resistance. So this is a patented system, but I'm pretty sure that there are some more players who are in the business of active isolation monitoring. So this will be our last slide, which will talk about an example for IMD. So this is a Bender isometer, and I may not be able to describe the internal functions since this is not what we designed, but basically someone had asked me, do you know that if there are systems available already in the market which are able to monitor the isolation in an active way? Active way means when the vehicle is running and even when the vehicle is stopped. Or so this is the system. This device will work when HV is not stable. This device will work when HV is powered off. This can measure symmetric as well as asymmetric insulation faults. And yeah, basically during measurement, it provides galvanic insulation. So because of its internal error, you're not going to introduce an isolation fault in the vehicle, which previously did not exist. It has a CAN bus interface so that it can be easily interface with other vehicle subsystems. All right, so this was all about isolation management. I am now happy to answer your questions. Thank you.
Hi. Thank you very much for the wonderful session. I have a question between the active and passive measurements. Where in the passive measurement we can measure the difference. I mean, we can to make the individual. We can assess the individual isolation resistance, like positive side and the negative side. But is it possible in the same like yeah RP and RN we can measure individually? Okay.
Yes.
But how about the active isolation monitoring? Can we do the same, or can we only find the parallel values of the RP and RN?
No, you can do both. In fact, you can measure separately the RP, measure separately the RN. And as
Okay,
I said, the advantage in active isolation monitoring system is you can do it even when the vehicle is running. In
okay,
passive system, this is a disadvantage because the voltage will be continuously fluctuating, and it
hmm,
would be very difficult to estimate on the basis of this voltage drop or basically this voltage divider network the value of RP, because this requires the voltage to be known on stable.
okay, okay. But that we can measure using this V3, right? What is the exact voltage on that time?
Yeah, correct. We can measure, but as I said, imagine the situation of running vehicle. The V3 will never be stable.
Okay,
So either you need to have some complex software, of course, that
okay,
is possible, with which you will have to do some sampling, some low pass filtering, and then estimate the value of V3 exactly at the time of sampling. Because
okay.
see, even when you press close the switch, it is not an instantaneous value that you are going to get because of
Correct.
the
Yeah.
complex capacitances.
Y
The
caps. Yeah.
time, yeah, Y caps especially correct. You are very absolutely correct. Because of Y caps and also because of all other parasitic capacitances.
Hmm.
So these are all
Okay.
parasitics. it is going
Okay.
to take longer time. So by the time if your VDC changes,
Mm-hmm.
then your system may not been accurately estimate the RP or RM.
Okay.
It
Okay.
may take 10 to 20 seconds in
Yeah.
reality.
Mm-hmm. Yeah. Okay. Okay. Fine. Yeah. Thank you.
Thank you.
Thus, Mr. Vijay asked, is it okay to have a common earth in the form of vehicle chassis for both AC and DC systems?
Is it okay to have a common earth in form of vehicle chassis for both AC and DC systems? So first of all, when we are using vehicle chassis as an earth, let me understand the question clearly. So the vehicle chassis is always with reference to low voltage, correct? So when we are talking about AC or DC systems, which is part of your question, we are talking about high voltage AC and DC, correct? So in that case, we cannot consider there is no galvanic connection between high voltage system and so maybe I'll use this diagram here. So this is the high voltage DC system, correct? And probably this is the high voltage AC system. This is the vehicle earth. So if the charger is not connected, then vehicle earth is not connected to high voltage AC system. I hope you are able to see my screen.
Yes, yes.
But maybe Vijay, if you can elaborate your question, or did I answer it?
Yes, yes. Right, right. That is what I wanted to know. Yes, sir.
Okay, thank you.
Thank you.
So I have another question here. So
Mhm.
you had mentioned about in your presentation about the higher voltage, the industry shifting to a higher voltage system. Right now we have the two-wheelers as well as the four-wheeler shifting to a higher voltage range. So now, how prepared is India in terms of the challenges that we have been meeting, or the industry setup, or the lab setup, or other? Is there any scope of improvement on what we've been working currently to what can be done better in future, working with these high voltage systems?
Yeah. One good part that I'm observing as an industry observer is this transition is happening step by step. So we are not directly jumping to 400 or 600 volt systems as in case of Europe or American OEMs. So the two-wheeler and three-wheeler industry, they are just jumping 12 volts at a time. So this actually gives us a lot of time to rectify or improve our systems. And of course, I don't see this to be a big challenge because the shift is happening gradually and with a smaller step of voltage improvement. So 48 to 60, 60 to 72, 70 to 96, and so much so on.
Uh, yeah, so makes sense. So there's one more question.
Mhm.
Now we see standardization has been an ongoing problem nowadays, like from charging protocols to battery development to more importantly EV safety. So all each one follows the own set of standardization. So we don't have a standard set of protocols that we've been following lately. So what can be done on these areas, you think, so that we can improve the robustness to previous issues that we're facing today?
Yeah. So we are always, I mean, we have an AIC in India, which is the apex body for upgradation of all the standards. And through ACMA channel or through SA channel, tier ones and OEMs are also part of this standardization body and part of standardization meetings. So basically the inputs coming from our fraternity are very well received by this body, and they are also part of the most recent version of the standards. In fact, I myself am also part of some of these bodies, and together we are ensuring that the standards which are part of India are state of the art with respect to global standards. Of course, there is always a scope of improvement, and as I said, uh, regulations are one step behind standards, but that is also maybe a decision which is taken in the wider geopolitical or economical context.
Yes, sir. So just a follow-up of this question.
Mhm.
So you were talking about the regulations that we have in India. So, like, does the regulations presently that are present now cover up all the needed part of the necessity for isolation? Do we cover
Yeah, so
everything that is
maybe
required? or if
So
there's more scope of it's something that has to be improved in certain aspects.
correct. So maybe I'll go back to my slide number 11. So regulation definitely needs the automotive supplier manufacturer to maintain isolation. And this is a very clear statement in the AS 038. Now, the question is about whether to have an active or even passive isolation monitoring device which is on board in the vehicle. So this is where think that further evolution of the standard will happen eventually. Right now, the standard says that the supplier should be able to demonstrate that the isolation is there either by isolation measurement test, which is part of this regulation, or by showing some calculations.
Yeah. Okay. So you were talking about isolation devices as well. So do we have any made in India isolation devices as of now, or is there somebody working on it? How is the situation there?
So we already have made in India isolation devices which are in the passive manner, including my own organization. But at least I'm not aware of any Indian organization who is dealing with active isolation monitoring device as on today.
Yeah, so from my side, so
Hmm.
hi, MS is Roshan from Device, and I have some questions regarding the charging system. Actually, in chargers, we do the isolation monitoring at DC side. So we
Hmm.
used in our case we used the Sendine one. The IMD come from the Sendine, not
Okay.
the bend. So that is for DC side. Then do we need from AC side also the insulation monitoring for charging?
Mm, yeah. No. Unfortunately, I may not be able to answer this question. I will have to check this because this is you're talking about the electric vehicle charging station (EVSE).
You're right.
Yeah. So yeah, I do not possess that subject matter expertise to answer this question.
Okay,
But
okay.
yes,
So
it depends on kind of EVSE system which we discuss here, whether it falls in TT or IT. Depending
so
on
it
that,
is if it is IT, then what can be the case?
then basic knowledge suggests that for an IT system, you should require an IMD, which is
Okay.
shown here in this diagram.
And what will be my reference point? Then against what point I am measuring that insulation?
So at least whatever I know, the reference point is always the equipotential bonding point. So whenever we are connecting a charging socket into the vehicle, we have to
Right.
first ensure that chassis of the vehicle and then the PE, the protective earth terminal of the charger, are uh, properly connected to each other. In that case, then the reference point will be the PE line.
Right, right,
Because
right.
PE line and chassis now are at equipotential level.
Okay. Then the vehicle chassis is connected to the LV ground. Then that can be a battery or a DC-DC ground, right?
Correct. Vehicle chassis should be connected to LV ground, the 12-volt battery, the standard 12-volt lead acid battery ground. And during charging, this should get connected to protective earth.
Then that protective earth no, is not coming from the grid. We are seeing like it is connected to direct earth, or from the earth we are taking, or the neutral, from the neutral we are taking that earth. So that earth is
Correct.
not the
Correct.
direct earth which is coming from grid. It can be also the LV side of the charger.
Could be because as I have mentioned here, in India, our earthing system is TNCS. So you can see in this diagram that this earth is connected. So they are not connected to the source side. There, that is a local earth.
Okay, right. So, if you want to means there is a voltage HV definition you told, like
Hmm.
60 volt and above 60 volt will be the voltages or the ratings. The particular vehicle should have the IMDs, or the insulation monitoring and isolation monitoring is mandated there. If we are considering the two wheeler, and if I am going to short or make the earth ground to the 48 volt ground, then what will be the case? Is it safe, or I can
Yeah, in
still go
fact,
with the
no, in fact, whatever architectures I have seen, even because 48 volt is also present in the mild hybrid electric vehicles, typically in Europe. So I have seen in those architectures that the 48 volt battery ground and 12 volt battery ground are shorted together, and they are also connected to chassis of the vehicle. Because as long as you're not creating a galvanic isolation between 48 volt system and 12 volt system, there is no need to treat these two grounds separately. So in your two-wheeler architecture or in any other vehicle architecture, as long as your battery voltage during charging also is not going to exceed 60 volts, you can safely connect that ground and the 12 volt ground to each other.
right, right. So okay, so most of the people are likely refusing to use the LV battery, extra LV battery to means supply the system. They are going for the DC-DC, and most of the DC-DCs are non-isolated, and the non-isolated one are actually their ground is common with the 48 volt. So so using that non-isolated DC-DC is safe, or the isolated one can be the good option.
Now, again, if the working voltage is below 60 volt DC, then there is no need for isolated DC-DC.
Right, right. Okay.
So you can use unisolated DC-DC, and then you can have a common ground, obviously, output ground and input ground.
Okay, so if the particular low voltage system, actually I'm taking a lot of time, but yeah, it is, I think, important from my side. But
Yeah, please.
if we are considering the BMS is running on the DC, the low voltage DC, and if there is any fault from the high voltage side, and we are making the ground common, then is it any miss? Is there any chance there can be a fault, and that can be, that is from 48 volt? I'm saying.
No, I mean, there could be some challenge with respect to EMC because
Right.
of the return path. But from, I mean, from the point of view of our topic, which is the safety, electrical safety, there is absolutely no challenge. But yes, maybe you will have to consider the EMC topics because maybe you're having a different path for return currents.
Right. Right. Thanks for clarification. Yeah.
Yeah, thank you.
Yes, Mr. Rajesh Kulkarni, you have a question you want to ask it?
Yeah, okay, thank you. So the question is a little bit more related to the recent news that we are, let's say, seeing the case of fires in the electric two-wheelers. So would there be any, let's say, direct relation, or would the insulation monitoring be a probable cause of these fires, apart from, of course, the details of cell chemistry and BMS and all of that?
Yeah, yeah. Thank you, Rajesh, for bringing this question. So as I have also highlighted here that electrical shock and electric fire hazard, or sorry, vehicle fire hazard, they are definitely linked to each other. One can cause the other and vice versa. Now, coming back to the observation that we have had in especially the electric two-wheeler industry in the last 2 weeks, I believe these were not using high voltage batteries. So there probably was no galvanic isolation that existed in the vehicle. But yes, if any of these vehicles or in future, if any of the vehicles start using high voltage batteries, then because of the compromise of isolation, there is definitely a chance of fire hazard. And from that point of view, it is very important to take the isolation management as seriously as we take the seriousness towards fire hazard or thermal runaway event in batteries.
Okay, thank you. Thanks for the informative presentation. Thank you.
Thank you, Rajesh. Good to see you here.
Yeah, I think almost done. We're done on 10 minutes past the scheduled time. So thank you, Mr. Gambhir, for joining us today. So any parting words from your side before we end the meeting?
I would like to thank you again. This was also a very good opportunity for us to increase overall awareness in India, and I'm really happy that we have a community of like-minded people, both from tier ones as well as from OEMs, and also from regulatory bodies. I saw some of the representatives. So my intention was to increase our overall awareness and then kind of create a sensitization towards this challenge, because probably our attention is only focused on fire today, but isolation, as I said, is an aging effect, and maybe the vehicles which are running today after 2, 3, 4 years, we might start seeing some of the effects if this was not taken very seriously at the time of design. So with that note, I would like to thank you again for this interactive session, and then I'm looking forward for some more sessions in future with you again. Thank you.
Yeah, thank you so much. Thank you, everyone. Have a wonderful time.